continue our study on the laws of cosines applications. Let's do a SSS triangle, meaning you're given three sides, no angles. Okay, so let's create like a generic example. Let's call this a little a, meaning this is capital A. Let's call this a little b, meaning this is capital B. And let's call this little c, meaning this is capital C. We know a is equal to 6, b is equal to 9, little c is equal to 4. Okay, so we only have the side lengths, no angles. We can use the law of cosines to solve for the angles. So we know one of them is a squared is equal to little b squared plus little c squared minus 2bc cosine of a. So we aspire to solve for a. So we need to send all the terms to the other side and divide by this to get cosine of a on its own. I get cosine of a is equal to a squared minus b squared minus little c squared all over negative 2bc. Okay? If you do the steps one by one, send this over, then send that over by subtracting them, and then divide by that, you get this. Then you take the cosine inverse of both sides to get what a is. It's the cosine inverse of this stuff right here. Okay? So, whenever you plug that into your handy-dandy calculator, you get the output of A is approximately 32 degrees. Okay? So we know A is 32 degrees. Unfortunately, we need two angles to solve for the third, so we do this process again for another one of them. So we'll do B squared is equal to A squared plus C squared minus 2AC cosine of capital B. And then we can solve for B by doing the same algebraic maneuvers. So B is going to be equal to the cosine inverse of B squared minus A squared minus C squared all over negative 2AC. Okay, that's cosine, and then you take the cosine inverse of that. And so then we get capital B is approximately equal to 127 degrees. Okay. So now we know what capital B is, and we know what capital A is, all right? From this point on, it's pretty straightforward on how to get capital C, right? Because in flat Euclidean geometry, the sum of the interior angles of a triangle adds up to 180 degrees. And we know two of the angles, so I get, this is equal to 32 plus 127 plus C is equal to 180, meaning C is equal to 180 minus 32 minus 127. That implies C is equal to, if I can calculate that correctly, C is equal to 21 degrees. So we solved that problem. We found capital A, capital B, and capital C. All right? So let's move on and let's do another example. All right? All right? Let's say you have three locations, a location A, a location B, and a location C. And these represent airports, all right? Let's, arbitrarily say this is New York, and this is Canada, somewhere in Canada, and A is, Alabama or something like that. So let's say you have an airplane that goes from New York to somewhere in Canada, all right? And let's say you have an airplane that goes from New York to somewhere in Alabama, okay? What is the distance from Canada to Alabama? What is this distance, okay? If we tell you that this distance is 650 miles, and we tell you that this distance is 600 miles, all right? We do need to tell you some more information. we need to tell you that if I draw a straight line like this, that this angle makes 60 degrees. And this angle makes 20 degrees. All right. And that's all I have to tell you. That's all we need to tell you, that these points right here. So now this is seeming like a cluttered situation. So I'll redraw this triangle so that it seems less cluttered. I'll call this B, C, and A. Notice that we aspire to find what little b is, okay? Because we know little a is 650, and we know little c is 600. What about this angle? Do we know what capital B is? Well, in a straight line, the amount of degrees is 180, all right? So because of that fact, you could say that this angle right here is 180 minus 60 minus 20. So 60 and 20 add up to give me 80. So when I subtract 80 from 180, that means this angle should be 100 degrees. All right. So I know that's 100 degrees. So I have a angle side problem. Okay. So we don't know this angle, we don't know that angle, but our true goal is to find little b. So using the law of cosines, we know little b squared is equal to little a squared plus little c squared minus 2ac cosine of capital B. Notice that we know what a and c are. It doesn't matter that we don't know what these angles are. That's the beauty of having more and more equations in mathematics. The more and more equations you have, the more and more tools you have to excavate truth. And sometimes it allows you to circumvent the lack of knowledge of certain things. So we don't even need to know what these angles are in order to figure out what the distance little b is. We can right away, using the law of cosines, calculate it. So notice that if I solve for b, I get b is equal to the cosine inverse of b squared minus a squared minus little c squared all over negative 2ac. We'll take the cosine inverse of that quantity. And, oh, wait, so actually, let me backtrack here. We want to solve for little b, not capital B. So, really what I want to do is actually, instead of doing that, I want to take the square root of both sides. I get b is equal to the square root of a squared plus c squared minus 2ac cosine of b. And I know what cosine of b is. B is 100. So little b is going to be equal to the square root of little a squared, that's 650 squared, plus little c squared, that's 600 squared, minus 2 times 600 times 650 times the cosine of 100 degrees. Once we compute that in our handy dandy calculator, what we end up getting is, if I can calculate this pretty quickly, what we end up getting is that little b equals 869. And we were talking about it in miles. So now, using this calculation, we are able to discern and deduce that the distance from Alabama to Canada, to some city in Canada, it's a fictitious city, okay? I didn't specify the city. Is 869 miles. So I called it Alabama and Canada and New York just to kind of give you a type of reference point. That's not the true distance from Alabama to some city in Canada. I was just using that to give you kind of like a reference, a geometrical reference of how to apply such a problem. We could, in fact, really get distances of geographical distances and do trigonometry and find actual distances using this. So just because I put in some points and variables does not mean that it was accurate to this scale, but we could use trigonometry to make it accurate on real scale.